Hello and welcome to my new playlist. So this is the first of a series of videos where I try and do things which I find are very fun ideas, but they're not necessarily very practical in terms of I couldn't commercialize these ideas or make apps out of them because the end results probably won't be robust or stable enough for widespread deployment. But as an idea, as an afternoon project, hopefully it will be good. So the idea that I first came up with was to take dot to dot, and I'm sure you're familiar with dot to dot. Here is an example of a dot to dot, and what you'll notice is that I haven't done any of these dot to dots. They're all undrawn, and then this is because I want to use computer vision and machine learning to do it for me. This is the best idea I could come up with for a project that I wanted to do. For me, doing that is very fun, and I hope you enjoy the process. So first of all, I'm going to take you through what I plan to do, and then we'll talk later and I will show you how I got on and how the results are going and the methodology that I used. So this is once again a project about doing dot to dots, and I've named it Join the Dots. It's easier on the ear. And what are our goals? So I'm sure you're familiar with what join a dot to dot is, but what we want to do to automate it is that we want to localize the digits and the dots in our image, and we want to read and understand these digits to form the numbers, and so we can then connect up the dots in the right order. So that's the final challenge, is to join the dots up in sequence, so we'd have something looking like this. And ideally we want to do it in real time, so we want to be able to update with the image several times a second. So you could imagine in a mobile phone or from a video submitted through a website or a web app. So the first thing we do is, in this first sort of trial run, is we do segmentation of our image. So I started by doing this in a sort of very basic way. So what I did is I took the images, and then I wanted to denoise them. I wanted to process them. So what I did first is inverted those images, and then I took a very heavily blurred image. This is something like a sigma of a Gaussian, so that's the width of the Gaussian, a sigma of say 30, which is quite large. And then I subtract the smoothed image from the inverted one, and what I get is a high pass filtered image. So this is an image where the sort of undulating sort of background noise has been removed, and I'm just, in this case, left with the details which I'm interested in. So then to do the actual thresholding segmentation, what I do is I apply an algorithm to the histogram of the image, in this case UTSU, and what this does is it reproducibly and reliably separates the background from the foreground set of pixels. It's a very easy to use and very straightforward and fast algorithm for finding a desired value to separate what is most likely background and foreground. So what we end up then with is a thresholded image, a binary image, where we no longer have a distribution of pixel intensities, we just have black and white. And then from that point it's pretty straightforward for, in the case of Python, the SK image library to isolate each of the, in this case, digits or features of interest, and encapsulate them with a bounding box. So this is sort of based on a sort of flood fill algorithm, which will come and find all of the sort of islands of intensity and parameterize their location. And so what we end up with then is every digit and a bounding box surrounding it, and also the dots. But at this point the algorithm doesn't know what is in each of the boxes. So what we need to do is find some way of classifying them so that we can say this form which looks like a 2 is a 2, and this is a 1, and this is a 4, for example. So for that we use a convolutional neural network, and we're going to use an MNIST style digit classifier, which is a very famous and very common form of neural network. And what this comprises of is a number of convolutional layers with other features, for example, like dropout layers, and also max pooling, and then it kind of finishes with a dense layer just to connect everything up at the end. And if you want to know more about convolutional neural networks, I have a link in the description which you can follow for more information. But what essentially happens is that each of these isolated digits or dots will be passed through one of these classifiers and the identity of the digit found. So, for example, it will quickly scan each one, and then we'll be able to, with a certain probability, estimate which of our pre-programmed digits it will be. So if it's a 9, it will scan it, and hopefully it will recognize that it's a 9. If it's an image of a 2, again, hopefully it will find that it's a 2. So this is all done in Python using TensorFlow library. This is code that I just downloaded off the internet. It requires some training. To create the training material, I actually had to label a lot of digits myself. So although you can have a pre-trained MNIST convolutional network, I found that it didn't work very well on my data due to its unique characteristics. So what I did is I create a script using the software Fiji, which is just very easy to use image analysis software. So what I did is I came up with a script which would basically allow me to label the data very quickly. So here I've got regions popping up, and then using the keyboard I'm just quickly labeling each form that appears, and labeling it with the number or that it's a dot, or if there is multiple things in each of these regions, then I just classified it as an F, which means just sort of fail. So in this way I quickly created high quality data from which to train the algorithm from, and then I proceeded to training. So to train a neural network, you need training data and labels. So we've created the training data, I showed you how I created the labels, and then what you do is, with the help of the script, you basically optimize the weights, the kernels in those convolutional layers, so that when you put in your digit, you get the right number coming out. And so when we validate it and then go on to test it, hopefully we get the right digit corresponding to the right input. And in this case I put the wrong ones there just to make a point that you can train it and it might not be very good, but ideally when you test it, the inputs will match the labels which you assigned when you labeled your sort of holdout test data in the beginning. But in our case it worked pretty well for the data that we were giving it. But that's only part of the problem. So once you've classified each of the regions, you have basically classified the individual digits or the location of a dot, but you haven't actually formed the larger number. So for example, you may know it's a 1, 3 or 2 and that there's a dot nearby, but you really have to be able to link those up into a contiguous region and associate them with the nearest dot. So that was the next challenge. So the way in which I did this, the way I thought about it, was to think of our numbers and dots as vertices on a graph. So graphs as in mathematical theory. So basically I assigned each number, each dot as a vertices, and then I found the best way to sort of link them up was to first of all add edges, just one edge at this time, joining each number to its nearest number, and that looks something like this. So you can see there are some areas where there's more than one connection, but that's just because each number has one vote. So sometimes there'll be the same two numbers will be each other's nearest neighbor, although this isn't always the case, as you can see. And once we've done that, I found the next best step was to find to add edges connecting each dot to its nearest number. And so now you can see that each sort of complete number and its dot is linked up, and I've done this just by assessing in two phases what the nearest neighbor was. And once you've got something like this, which basically is a directed graph, then it's pretty straightforward using conventional graph theory Python libraries. You can join up the vertices along the edges, and what we basically want are the neighborhoods, which look something like this. So these are the sort of contiguous areas of the graph which are all joined up, and that equates to our numbers and associated dots. And then it was basically just a standard task to say, well, I'm assuming that the start of the number will be on the left hand side of the scene. So if you showed this dot to dot upside down, it wouldn't work very well, because it would be trying to classify numbers that are back to front and also on the wrong side of each other. So one of the assumptions that I've said is that the dot to dot has to be presented more or less the right way up, but I think that's a reasonable assumption to make. And well, it does actually work. So although it doesn't get everything right, so you can see, like in this example here, the finger isn't quite right on the lady and some of the aspects of the face, but you can definitely work out that it's a lady with a microphone and a bird. And then with this technology, it becomes possible to basically evaluate very quickly what each of the dot to dots in our book was, and in general. And what I found is that there's sort of quite a unique combination of objects which finds its way into a dot to dot, and I don't think the authors ever really expected someone to just go and sort of mass do them and then present them on the internet. But this is definitely a new hobby for me. So you can see in this section I've aligned connected the musical instruments, and you can see that you can recognize what they are, but there are certain things that are sort of just missing, and that's the fault of my algorithm, and that it didn't quite catch those numbers, so it wasn't safe to draw lines in between them, but you can definitely recognize what they are. And here we've got some musicians actually playing instruments. And then we have some more bizarre categories, for example, animal husbandry. People from the countryside working with their animals. Maybe this represents a key kind of duo of dot to dots. And then there was a sort of Easter theme, or rather a consumption of Easter goods during Easter. Maybe a sponsor of the book, I don't know. And then a sort of interest in birds and fowl. Somewhat of still of an Easter theme. And then there are some sort of miscellaneous objects which weren't so clear. These were probably the ones just left over and put in the book. Heavy machinery and rucksacks. So one thing that I did was I introduced a few sneaky heuristics to get it to work a bit better. So you can see in this untreated image on the left, you can see that there's a line that kind of crosses the face. And I just found that occasionally this would happen if a number was misclassified. It would often connect lines where they didn't really seem to make sense. So I just said if one line intersects another of other lines, then it's probably not a true line, because in dot to dot it's quite rare, or it's much less frequent that lines actually intersect one another. They generally sort of go close to one another, but not across each other. So I just said if you find any lines that have a high intersection rate, then remove them. These are likely to be false positives. So if you do that, then you get an image which is less offensive on the eye, but you can see we've actually lost some other details where lines were quite close to one another. But I thought that a reasonable rule to apply. And then some other limitations. So this doesn't work well, unfortunately, for video. So although it's quick enough for sort of real-time use, it's not perfect. And you can see on the left that it quickly loses the points due to motion blur and due to out of focus areas. And on the right hand side, I've got an image which I took a photo of, and the illumination wasn't very even. So again, it's not working very well there. But that's not a problem which is unsolvable. In this first run, what I've done is basically used signal processing to do my segmentation, and this is quite a kind of specific method based on high quality images. But it's not impossible for example, a human to recognize these numbers as they're moving around. In fact, it's quite simple. But the blurring and the motion blur do cause problems for an algorithm based on such a simple segmentation method. And so it is possible using machine learning to basically come up with a way of identifying the regions for classification which is more tolerant to these kind of visual artifacts, and it will do that in a much more kind of numerically intense way, which will require training and require sort of fine-tuning. So I didn't do it this time because I just wanted to keep it light and try something out. But if you like this video and you want me to show you how far I went with the machine learning, please like it and comment, and I'll be happy to show you where I've actually applied things like object detection and specific text recognition algorithms to do this. And then we'll get much closer to our goal of being able to do dot to the dot in video. So thank you for now, and yes, if you did like it, then please like the video, and I'm happy to follow up with more. Otherwise, I will follow up on a new topic. So thank you very much.